we continue, and this is lecture 5.4, and now I want to discuss projective space further. Part 2. So we have this projective transformations, and the first question is, okay, how rich is the group? What you can do with it? Can you send any 4 lines to any 4, any 3 points to any 3? So here is the theorem. So let me formulate the main result immediately, and then I will just give examples. So theorem. So suppose that you have Pn minus 1, and you have 2 collections of lines. So L1, Pn minus 1, L1, Ln plus 1, and M1, Mn plus 1 are so these are lines in general position. So what does in general position means? It means that any n lines, sort of L1 to the without Li up to Ln plus 1, so these are n lines, and this is a projectivization of an n-dimensional space, V, span V. So I remind you, these are one-dimensional subspaces, almost like vectors, and you want them to be linearly independent. Yeah. So these are 2 sets of lines, n plus 1 lines. So then there exists a unique phi inside P, G, L, N, PGL, projective transformation of our space, such that phi of L1 equals to M1, and so on. Phi of Ln plus 1 equals to Mn plus 1. So there is a unique transformation sending all these lines to all these lines. Okay, so let's look at some examples. So the main one for us right now will be an example where we take P1, and then, okay, so this is projective line, and we call lines, we call them points here. So here n is equal to 2, and so any 3, and when lines in 2-dimensional space are 2 lines span into, when they are distinct, any 3 distinct points can be sent to any 3. So that's completely remarkable. You take some projective line, which you think as line plus this infinity, you take another copy of that, and you have your favorite point, I don't know, 1, 2, 3, and then you can just, pick. You can send this one here, this one here. So that's what it looks like. Any 3 points go to any 3. And if you do P2, so now if you do P2, which you can also imagine as usual plane, but just, there is some infinitely far away stuff here and there, and then you can take any 4 points and send it to any 4. If no 3 are on the same line, which means that 3 corresponding lines are not in the same plane in 3D. So with usual linear transformation, or what's called affine transformation, you can send like 2 points to 2. And here you can send 3 to 3, 4 to 4. So it's very, very rich group. So there are tons of interesting theorems in geometry where you can apply it. For instance, there is this famous Pappus theorem, which tells you that you can, if you just take 2 lines and 3 points of each and connect them in some pattern like this, then the corresponding intersection points lie on the same line. And that's a hard theorem, and you can prove it using projective transformations by picking some 4 points on the picture and sending them to 4 vertices of a square, and then the whole picture becomes much simpler. I don't know, but you can use elementary geometry to prove that. So I didn't explain that. This is just an idea. And please, if you have never encountered projective geometry, I highly recommend you during the break just spend several days reading about it, looking at these elementary geometry problems, visualizing this P2. That's remarkably beautiful subject, and it's helpful in many areas of math. So this is a theorem in linear algebra. Let's prove it. So proof is pretty straightforward. That's standard linear algebra. So proof. Let me prove existence. So existence. I mean, we have lines L1, Ln plus 1, lines M1, Mn plus 1. And let's suppose that Li is a spanned by vector Vi, and Mi is spanned by Wi. So we have some vectors inside these lines going. And then, I mean, you know, we are almost there because we are living in n-dimensional space. We can send any, wait. What? We are living in n-dimensional space, and we can send any n vectors to any n vectors, which are linearly independent. So we know that any n of those are linearly independent because of this condition. So there exists a linear map, let me call it psi, such that psi of v1 equals w1 to the psi of vn equals wn. And of course you imagine that this means, of course, psi sends lines to lines. And that's it. So in usual vector space, you have no more freedom. But in projective geometry you have, because you can rescale them. So you can send V1 to some rescaling of W1 and still get the same space. So let's just now suppose that Wn plus 1 equals x1 W1 plus and so on xn Wn. We just write it as a basis. In a basis, and Vn plus 1 equals y1 v1 plus Vn wn. So we just write both remaining vectors in a basis, and notice that, observe that all these numbers xi and yi are just not 0. Because if they were 0, we got a linear dependence between some vectors here, with coefficient 1 here, so not trivial. And because any n lines out of this or this were in general position, that never happens. So all these numbers are non-zero. And then let's just take phi of v1 sending v1. So I want to send it to some rescales w1, so that let's see. So I want to send it to, v1, I want to send it to x1 divided by y1 w1. x1 over y1 w1, and so on, phi of vn equal xn over yn wn. So we just send our n vectors to n vectors, and then of course from here we just see by applying this transformation that phi of vn plus 1 equals to wn plus 1. Just because, just see. This goes to here, this goes to here, and so on. But then, of course, phi of L1 equals to M1 to the phi of Ln plus 1 equals to Mn plus 1, and we won. So done. And uniqueness is completely similar. So for uniqueness, you just imagine there is a map which actually fixes all of them up to rescaling, and and then you can, using linear dependence, prove that the uniqueness part. That's very simple. Maybe it will be one of the homework problems. So let's consider this theorem proven. And now I want mostly to use this kind of part to illustrate how we can apply this to understand better sizes of projective transformation groups and to understand maybe this PGLN for small n. Okay, so let's start with at least understanding size of everything. So now I take f being fp. So f being fp, and then I have a projective line p1. And what is p1? So as a set, you just take fp and then one more point. And so the size of this thing is p plus 1. So whatever our PGL2 of fp looks like, it acts on a set with p plus 1 elements. Okay, so let's try to figure out what is the size of this group. So for that, firstly, let's consider GL2 of fp. So GL2 of fp, I mean, what is the order of this group? So how to count this order? I mean, last time we did this PGL2 of f2 and we looked at 2 by 2 matrices and actually counted them, but it's much more simple to say that, you just need to choose 2 linearly independent vectors in fp squared. And how many choices are there? So for the first one, you have p squared minus 1 choices. And now you have chosen one vector. And you choose any vector except 0, because, any vector like that will be a pair of, first one in the pair of linearly independent vectors. And then you have the whole subspace. And the subspace which is generated by this vector is, again, a copy of fp. So it has p elements. And you need to choose anything except a vector there. And so that's why you get that this is just p squared minus 1 times p squared minus p. So that's the order of this group. And, good. What is the order of PGL2? So PGL2, this is just a factor group. And it's a factor group. Let's see what is the factor. So scalar matrices are just copy of like this guys, and they are just fp multiplicative group. So the order of this thing is p squared minus 1 times p squared minus p over p minus 1, which is p times p minus 1 times p plus 1. And you see for p equal to 2 there was no difference, because for p equal to 2 you don't factor over anything. But for p equal to 3 already there is a difference. So PGL2 of f3. So this thing has order 3 times 2 times 4, which is 6 times 4, which is 24. And fact is that PGL2 of f3 is just isomorphic to S4. So how this is the case? Let's just see. Okay, how to prove that? So first we need a homomorphism to S4. Where to get it? I mean, PGL2 of F3 acts on P1 of F3, which has 3 plus 1, which is 4 elements. And so, so it acts on 4 elements, and so we have a homomorphism PGL2 of F3 to S4. Let me call it F. And then there are two different ways to show it's bijective. So one, you can look at the kernel of F, and these are projective transformations. Projective transformations fixing all points all 4 points. But by our previous theorem, I mean, in this particular case, we are living in the case of P1, and we know that even fixing 3 points, it's already trivial. So fixing all points, then it just means that F is identity. So that's how you can prove so it's injective, so it's bijective because the size is the same. Size is 24, right? So that's one proof. But also there is another proof, because you can say, okay, so let's prove it's surjective. And then you have, you know, points 1, 2, 3, 4, and since we are, by previous theorem, we know that there exists a projective transformation sending any 3 points to any 3. But of course, if you know where 3 points go, you know that where the 4th point go. So if you know that you can send any 3 to any 3, then you know that you can send any 4 to any 4. Just forget about the 4th, look where 3 should go, and the 4 will go along with it. So we can use previous theorems in 2 different ways to prove that this is a bijective. An isomorphism. Okay, so you might start think maybe that the pattern, maybe PGL2 of F 5 is S5. Let's look at size. So size of PGL2 of F5 is 5 squared minus 1 times 5 squared minus 5 over 4, which is 6 times 5 times 4, which is 120. So that starts to look plausible, and theorem is that this is isomorphic to S5. I will prove it in a second. Before that, let me just say that here the pattern breaks. So PGL2 of F7 is a very, very interesting group, but it has nothing to do with S7 or S8. I mean, it has something to do, but it's not in any way isomorphic to it. So these groups PGL of something are very interesting, and they form a family which is in many ways similar to SN family, but I will explain this a little bit later. Okay, so theorem. PGL2 of F5 is isomorphic to S5. Okay, so let's prove it. So proof is based on the following idea. So we have already something along these lines, because we know. So PGL2 of F5 acts on P1 over F5, which is just this line with 6 points. So this is a set. I mean, I can call it, you can think of it as 0, 1, 2, 3, 4, infinity. You can think of it as acting there by these fractional linear transformations we discussed. So we have a homomorphism. Homomorphism from PGL2 of F5 to S6. And again, we know by theorem above, if such a transformation fixes 3 points, it's trivial. Well, definitely it means it's injective. So, because if it goes to identity here, it fixes all points. So this is injective. Injective. So, PGL2 of F5 is isomorphic to a subgroup of S6. And I can say with 120 elements, but I will say just of index 6. And then here is how we prove the theorem. So fact is that every subgroup H of S6 of index 6 is isomorphic to S5. And you know, this is exactly this phenomena which was discussed in homework, this exceptional embedding S5 into S6. There is this homomorphism embedding S5 into S6, and why it's called exceptional, because I mean there is a very trivial one. So if you take S5, of course you can embed it to S6. You can just say, okay, just look at permutations which fix 6, for instance, and then you have something in S5. But the problem is that this is not one of those, because if you think about it, you know that, you know, by a projective transformation, you can send any point to any point, in particular, I mean, any 3 to any 3, in particular, any point to any point. And so this cannot be one of those. And actually, the fact is that there are 12 subgroups of index 6 in S6, and 6 of them are these guys, and 6 of them are appearing from such construction. So that's an embedding of S5 to S6, but not the standard one. Anyways, it was just a comment. So now let's prove it. So proof of this fact is a little peculiar. So let me explain that. So consider 6 cosets. H, X, and then let me say G1H, G2H, G5H. And this will be G0H, where G0 is identity maybe. So there are 6 cosets, let's write them down. So this is a set with 6 elements. H acts on this set by left multiplication. So that's a non-trivial idea. Let me explain. So you can take any element in your subgroup H and any coset GH, and then you can take H, and the action does the following. It just multiplies, it looks at the coset of element HG. And I mean, the fact that such action exists is completely trivial. Of course, you can multiply cosets on elements of H, and of course, starting with a coset, you will get a coset. You can even take elements of G or whatever else. So that's not surprising. But now we have an action of H on the set with 6 elements. And moreover, we know that this one goes to identity. So H times H is H, because H is a subgroup. So there is a fixed point, and it means that actually H acts on these 5 elements. H acts on the set G1H, G2H, and so on. G5H. Perfect. So it acts there. So we get a homomorphism from H to S5. So why S5? Because there are I mean, H has index 6, and there are 6 permutations of the set. So we get index 6. There are 5 cosets, it acts on them, so we have a homomorphism to S5. Let me call it F. So what is the kernel of F? Okay, let's look at it. So kernel of F is the set of H in H which fix every coset, such that H, G, H is GH for every G. But that means that this is a set H in H, and then if you just expand it, you will see that it means G inverse H G is inside H. Or you can say, let me erase this part. Or you can say that this kernel of F actually equals to intersection. So this is H in H, such that H is inside GHG inverse. So for every G, but this is just intersection over all G in G, groups G, H, G inverse. Fine. I mean, put attention, because I mean, such things are, so we have some interesting map, we look at its kernel, we get some interesting group. I mean, that's all kind of little non-trivial steps. And this is a subgroup of H, and in particular it's a subgroup of H was inside S6, so it's a subgroup of S6. And this subgroup is normal. So this is normal in S6. That's very simple. I will leave it as an exercise. It's a little exercise. I will put it as an exercise in homework. That's really simple. But intuitively, just imagine you take element here, you conjugate, and it was all in all these groups, and these groups get permuted, and so, I mean, it will stay there. So that's easy to show it's normal in S6. But S6 is simple. Oh, sorry. S6 is not simple, but what I wanted to say. So it's normal in S6, and we know that there are just 3 normal subgroups in S6. So normal subgroups in S6 are normal in S6 are okay, A6, and that's huge. You know, and we are looking at a subgroup of H, which has already order 120, and A6 has 6 factorial over 2, S6, and identity. And since it's also inside H, then of course it means that this kernel is trivial. But this means F is injective, then surjective. So F is injective, but then finite sets, so the same size. F is surjective. So F is an isomorphism. And that proves the theorem. So you see, that's kind of a completely peculiar proof. Of course, you might say, but why don't I just write down corresponding permutations in S5? And that's an honorable task. Please do that if you can. That takes a little work. It's not easy. It's not simple, but it shows you a lot about the structure of S5 and this PSL2 of F5 and how they interplay. That's very interesting. Okay, let me now briefly address what happens next. Okay, so maybe before even doing anything next, let me just ask a little question. So what about sign? I mean, so we have a, so let's look again at this PGL2 of F5, for instance. We know that that's the same thing as S5. But we know that there is a homomorphism from S5 to, let's say, S2, which is, or maybe, sorry, let's better say, maybe plus minus 1, let me say, which is sign. How to think of it in this way? And I mean, at first you might say, okay, there is a homomorphism from GL2 FP to FP times, which is the determinant, right? And I mean, it's kind of clear that determinant should be related to sign. But the problem is that though there is this homomorphism, I mean, it takes lambda 0, 0 lambda to lambda squared. So it doesn't give you a homomorphism from PGL2 to plus minus 1. That's just because, I mean, these elements in the kernel don't go to identity, so that's why I mean, it's not homomorphism from here to here. But there is a homomorphism, but there is a homomorphism from, one can do the homomorphism from GL2 F5 to F5 times, and then to F5 times modulo squares. So if you wish, that's kind of Legendre symbol. So you just, basically what you do, just say by hand, okay, 1 goes to 1, 2 goes to, 2 is a square, mod 5, 2 square is -1, so 4 goes to 1, and this goes to kind of -1, and you just say by hand this composition. So you look at determinant of a matrix, you look what it is, plus or minus 1, and you get it. And this homomorphism takes a matrix lambda 0, 0, lambda, and certainly sends this to identity, because you get a square. So there exists a homomorphism from PGL2 of F5 to this F5 modulo squares, which you can think as determinant plus Legendre symbol. And that's, honestly, this is universal property. You want a homomorphism from PGL2, you better have a homomorphism from GL2, which kills the kernel, which kills this scalar matrices. So definition. So if you have arbitrary field F, let's say Fp, so then there is a group which is called PSL2 of Fp, and that's in general just constructed in the following way. You take, it's a kernel of the map PGL2 of Fp, and you send this to, sorry, Fp to Fp times mod Fp times squared. So just the same thing, and that's called PSL2 of Fp. And why this is interesting? Because there is this main theorem. So theorem, which I'm not going to prove, is that PSL2 of Fp is simple for p greater than 3. So for instance, for p equal to 5, you get so you get something inside S5, kernel of sine, you get A5. By the way, you need to prove that that's the case, and I have not proven that sine is the same as its determinant, but one can do that. And the reason is, you can just argue that it's a map from S5 to a group of order 2, so the kernel has to be a subgroup of S5 of index 2, there is just one. So that's why these groups are so interesting. They're simple. And before we had only one family of simple groups, just AN, and this is another. And they start to be different for p greater than 5 prime number. So what's the next example? Let's look at PSL2 of F7. And that's, by this theorem, it should be a simple group, and we can look at the order, and this is 7, 7 minus 1, 7 plus 1 over 2, which is 7, 6, 8 over 2, 7, 3, 8, which is 168. And this is an incredible group. So PSL2 of F7 has 168 elements, and it acts on 8 points. You have a homomorphism from it to S8, but it's very, very far from being bijective, because it has 168 elements, and 8 factorial is very big. Okay, so suppose we now look beyond this picture. So this was for PGL, PSL, projective line. Let's now look to the first example of such a group in projective plane. So for this, it's convenient to consider the case plane over field with 2 elements of size, plane over field with 2 elements. Okay, so now let's kind of look slightly beyond. So let's take projective plane on field with P elements. So these are lines in FP cube. And so the simplest way to count them is to just use the logic we did. So that's the same thing as you just take as a set, all vectors except 0 vector. And then you factor over equivalence relation where, so people say just FP cross, because you sort of factor over equivalence relation XYZ is the same as lambda XYZ. And I mean, so the number of vectors is P cube, so the size of it is P cube minus 1. And then the number of, so every vector is inside an orbit with P minus 1 other elements. So you divide over P minus 1 and you get P squared plus P plus 1 elements. So let's look at the simplest example, P2 over F2. It has 7 elements. So it has 7 elements, and there is a very cool way to draw it. So let me draw it, and the picture is like this. So you take kind of a triangle, and then you have 6 points, 1, 2, 3, 4, 5, 6, and one more here. And now I draw, this is pure combinatorial picture, don't think of it as actual real plane. So this 4 vectors, 4 points, are just elements here. And honestly, projective plane here, since there is nothing to factor over, there is nothing here, so you can think of it as non-zero vectors in 3-dimensional space. But I will label them in these homogeneous coordinates. For instance, I have a vector 0, 0, 1, 0, 1, 0, 0, 1, 1. And why I draw them on the same line? Because they lie on the same line. So they lie. So projective. So this is projective plane. You think of it as points in the plane, and lines corresponds to lines in 3D lying in the same plane. And these 3 lines lie inside the same plane given by equation x equal to 0. And similarly, you can just reconstruct the whole picture. So you can just draw all points everywhere here, and this will be exactly 7 planes. Sorry, 7 planes in FP cube, 7 projective lines. So these are points, these are lines. That's the picture of the plane, and that's called Fano plane. And we have a group of projective transformations. So PGL2 of 3 of F2. And now we are interested in where we can send. So we have now 3-dimensional space, and we need to so how many elements are there? So we need to choose. So in general, if we want to count GL3 over FP, then we need to choose a non-zero vector, and then we need to choose any vector not inside the subspace spanned by it, and then we need to choose any vector not in subspace spanned by the first 2, and then the size of this group. And if you want to look at PGL3, of course, this is just when you divide by P minus 1. That's just P cube minus 1, P cube minus P, and then you can say, so this was P cube minus P squared, you can say P squared minus P. So let's take P equal to 2, and then we get 8 times P cube minus P is 6, and P cube minus P squared is 8 minus something wrong is happening here. Oh, sorry, P cube minus 1 is 7. P cube minus P is Yeah, sorry, and here you get p cubed minus p squared over p minus 1 is p squared. P cubed minus p is 6, and p squared is 4, and so you get 7, 3, 8, and you get again 168. So there are 168 transformations, and they will all do something with this picture, so that all the lines in the picture, including the circle, will go to points, lines to lines. So all combinatorics will be preserved. Notice the number is the same. So actually, theorem, which I'm not going to prove, it's more complicated and involves kind of tricky combinatorics. PSL2 of F7 is isomorphic to PGL3 of F2. So somehow, miraculously, these two groups are just the same. As I mentioned, this group is simple, and this is smallest simple group after A5, and which is not cyclic. So I don't take Z over PZ. So basically, it's the second interesting simple group. You have A5 with their 60 elements, very important. The next one is this one. And there are two instances how it appears. And then you have a whole family. PSL2 of F7 are all, and F whatever else, FPs are simple. And from PGL3, you can do also this PSL3, and this family will be all simple. And so there are like lots of, these are families of simple groups, and you can take higher n, other fields, and you get lots and lots of interesting simple groups. Mostly they are distinct, but in low dimensions there are a lot of these miraculous coincidences, and this is one of them. Okay, so next lecture we go to this classical subject of Sylow theorems and kind of structure of groups and classification of groups. Closer to the end of the course, we will prove that, for instance, A5 is the only simple group of order 60.